Hi, I am Sebastiano D. Covone. I am a sophomore student at the University of Naples Federico II and I'm competing in the Quantum Future Challenge. In the last weeks, I explored the behavior of Bose-Einstein condensate simulated with Composer. The interactions of the atom inside the condensate give rise to non-trivial system dynamics. So, the main focus of this report is the study of this behavior for different regimes of interaction. Then, from the study, I derived some possible application on quantum optimal control problems involving Bose-Einstein condensate. In single particle scenarios, the Hamiltonian used is just given by the sum of the kinetic energy and the potential energy operator, and this is a linear operator. When we want to study Bose-Einstein condensate, we have to consider also the interaction between the atoms. This interaction is considered in the Hamiltonian with the addition of a nonlinear term. This nonlinear term depends on the parameter beta that describes the strength of the interaction. In a new Flowfile, I studied how the shape of the probability density function of the ground state for the condensate changed as a function of beta in an harmonic potential. The sign of the parameter beta determines the type of interaction in the condensate. For positive values, the interaction is repulsive and the gas tends to spread out. For negative values, instead, the opposite happens, since the interaction becomes attractive. For large beta, I also observed the validity of the Thomas Fermi approximation, and more details can be found in the report. This fact means that for large values of beta, the composer gives us back the right physics, and then we can proceed on a more solid ground. The nonlinearity of the Gross-Pitayevsky Hamiltonian gives rise to non-trivial dynamics even for the system eigenstates in time-independent potentials. A very easy calculation, indeed, shows us that the energy uncertainty is proportional to beta. This fact, combined with the Heisenberg principle, tells us that there is a finite time delta t for the system to change substantially without external perturbations. More details can be found in the written report. This flow file was created to analyze the dynamics of a Bose-Einstein condensate in the ground state of an harmonic potential. The three scalars at the top of the screen are the initial time, the final time, and the time interval dt in which I want to compute the functions of interest. In the fidelity node was calculated the fidelity between the state at the start and at the end of the evolution time. Fixed an arbitrary threshold for the fidelity, in this case was 0.7, I measured the first final time at which the computed fidelity is below this threshold. Those final times then were plotted as function of beta for both harmonic and harmonic potentials. The results are discussed in detail in the written report. This plot shows the dependence of the time of evolution described before as a function of beta for a ground state of Bose-Einstein condensate in both harmonic and harmonic potentials. As we see, both these trends are proportional to 1 over square root of beta. The theoretical reasons for that dependence are explained in the written report and are due to the Heisenberg uncertainty principle. My idea is that this threshold time of evolution can be thought as an upper bound for final control time in quantum optimal control problems involving Bose-Einstein condensates. Indeed, in the great flow chains for the Bose-Einstein condensate trapped in an harmonic potential, for time of control greater than this bound, we cannot achieve unitary fidelity. This bound became smaller for growing values of beta. This means that strongly interacting Bose-Einstein condensate are very difficult to control. Obviously, the choices that led to the measure of these bounds were arbitrary. But the idea is that, ideally, we can define a maximum control time in which it makes sense to try to control the Bose-Einstein condensate. This maximum control time is then strictly related by the Heisenberg principle to the parameter beta of interaction.